Welcome back, everyone. Today, we're going to start the last cycles we'll look at in this Introduction to Thermodynamics course for mechanical engineers. Specifically, we'll be leaving heat engines behind and looking at vapor compression refrigeration and heat pumps. So the question is, do you want to build a snowman? So remember when we started looking at cycles, we were talking about open system analysis. And we needed to do something like conservation of mass on a control volume, conservation of energy using the first law, and then we learned that you can't always get what you want, or that the second law introduces irreversibilities into every process. And while we have rate equations for the second law, we also talked about statements about the second law. We know that Kelvin and Planck told us that it was impossible to construct a device which operates on a cycle and produces no other effect than the production of work and the transfer of heat from a single body. If you remember, I told you I found the wording of this definition a bit confusing. But what it means to me is that we can take a cycle, we can make a machine that takes heat as an input and outputs power, but only if we're also rejecting heat from that engine to some cold reservoir. This is great if we're trying to make heat engines. And we've been talking about lots of different heat engines in this class, from Rankine cycles to internal combustion engines to Brayton cycles to turbojets. And in those heat engines, we're taking heat and turning it into mechanical work. And in a Rankine cycle, what we learned was a lot of times when we're a mechanical engineer, we use that heat to boil water. And when we boil water, we can get steam that expands across a turbine, and we can use that to turn a wheel. That was basically the core invention that gave us the locomotive. But at a similar time, there were people also looking at how we preserve food. Some people would salt food, so things like meat, you could store it in salt, and that would preserve it. You could smoke meat, which would preserve it. You could also have something like a cold cellar where you would can materials and keep them cold. So this is probably just my own imaginings, but I kind of think of somebody like Clausius then coming around and saying, well, those cold rooms are nice, but can I make a machine that makes a room, or at least some small space, cold so I can store food? And Clausius' statements of the second law tells us that it's impossible to construct a device which operates on a cycle whose sole effect is the transfer of heat from a cooler body to a hotter body. Again, I think that the wording here is not great and kind of confusing. But what it means is I can make a machine that has a cold half that's colder than my cold reservoir. What that lets me do is remove heat from this cold place. But then I also have to have another half of this machine that's hotter than my hot reservoir so that I can reject heat from this half of the machine into the hot reservoir. But I can't do that and produce work. I can't even do that and break even. If I make a machine like this, which looks like a refrigerator or a heat pump, then I have to plug that machine into the wall. It requires input power for this to run on a cycle. And that brings us to the vapor compression refrigeration cycle. So this cycle also consists of 4 components. They're open system components, just like we saw in the Rankine cycle and in the Brayton cycle. But the order here is a little different. When you look at this, it's almost like a Rankine cycle that's run in reverse. On our cold side, we have an evaporator, because now our working fluid, it's not water, but it's something like water in that it's moving back and forth across a vapor dome. Instead, it's some refrigerant. Now, this refrigerant evaporates at a temperature that's colder than our cold space. So it can accept heat from our cold space, and that evaporates our material. Now we're going to run through a compressor to increase the pressure, and now we're going to condense our vapor into liquid as we reject heat from our condenser to our hot reservoir. Now, in a Rankine cycle, if we were really running this as a Rankine cycle in reverse, we would have a turbine here. But we don't have a turbine here. Instead, we have an expansion valve. So we move through this expansion valve, whose purpose is to reduce the pressure, just like a turbine would. And then we're right back ready to get to the evaporator. In a refrigeration cycle, it's the evaporator that's the key component here because it's removing heat from the cold place. Right? And that's what we want in a refrigerator. Even though the air in your fridge is colder than the air in your kitchen, we're still able to remove heat from the air in the fridge and expel that heat into the air in your kitchen. So here, the key thing about the refrigeration cycle is our perspective. So if we were drawing sort of a person or a perspective here where we care about the heat transfer, for a refrigeration cycle, we care about the heat that we're removing from the cold side. That's the heat that goes into our evaporator. If I was drawing out a vapor compression refrigeration cycle, I need a vapor dome. When I have heat transfer components that are called an evaporator or a condenser, that tells me that I'm changing phase. So this working fluid works a little bit like the working fluid in a Rankine cycle. Right? So we're evaporating fluid by adding heat, and then we'll condense it by removing heat. Although it seems a little bit backwards when we compare it to a Rankine cycle, because here we're adding heat on the cold side and we're removing heat on the hot side. But if I construct a refrigeration cycle where I'm condensing from a saturated vapor at state 2S to a saturated liquid here at my high pressure, then that would be the process through my condenser. If my compressor was isentropic, then the inlet to my compressor would be vertically below the outlet of my compressor, which is state 2S. Now, as I go through my expansion valve, I'm deliberately drawing this line here on my TS diagram not vertical, because this process from state 3 to state 4 is not isentropic. We'll see in a bit that it's actually isenthalpic, but we'll describe that as we move through these different components. Next, in my evaporator, I'm heating this fluid up so that it goes from, in this case, some lower quality to some higher quality as I move through my evaporator. Then I go up through the compressor, and I can run in a cycle. Here, I'm putting work in at the compressor. Remember, you have to plug your fridge into the wall, so we have to add power to this cycle. We expect the net power, in this case, to be negative because we have to plug the fridge into the wall for it to work. We're rejecting heat on the hot side, which is different than all of the other cycles that we've looked at. Now, if we think of our valve, we don't really know how to solve this one yet, but if we think of our valve as a turbine, then we would be producing power at the turbine. And we add heat at the evaporator as we move from state 4 to 1. So this refrigeration cycle is a 4-component cycle, and it's moving back and forth across the vapor dome. So even though the working fluid is going to be some kind of refrigerant, it's not water, but we fix states similar to the method that we use for water because we're moving back and forth across the vapor dome. Here, because this is not a heat engine, this is some sort of temperature controlled device, the way that we characterize performance is different than thermal efficiency. So now our energy benefit is removing heat from the cold space. So this is the heat that goes into our system at the evaporator. The cost that we pay to run this cycle is not heat in, like it was in a heat engine. In this case, the cost of running this cycle is that we have to plug it into the wall, that we have to put mechanical power into this system at the compressor. So here, our coefficient of performance, denoted by beta, I kind of remember that we use beta for refrigeration cycles because this beta looks a little bit like a capital R, at least if I squint. So this is beta and not gamma, which we'll use for heat pumps. So here, our characterization parameter is called coefficient of performance. It's not an efficiency because it's going to be greater than 1, but this is going to be the heat that we remove from the cold place, or that goes into our cycle at the evaporator, divided by the cost, which is the net power. If you're wondering how I find these different terms, you're right in that I would do a first law analysis on all of these different components. We'll say that they're all at steady state, that they're one inlet and one outlet. We're not splitting the mass like we did in Rankine regeneration. We'll neglect changes in kinetic energy, so it's not like a turbojet. We'll neglect changes in potential energy. And then for each component, we'll think, is this really a component that's doing a heat transfer, or is it adding or removing power from my system? We'll assume that there's no friction or heat losses in between the lines. And when we do that, we'll find that the power from the compressor is m dot times h in minus h out. The valve, I'm still not sure. I'm going to call this adiabatic, right? So I don't think that there's any heat transfer from the valve. And if I do that, I'm left with this expression for the power that's produced by the valve. Because remember, I said the valve is a little bit like a turbine because we drop pressure across this valve. So I'm going to leave this expression for power from the valve as m dot times h in minus h out. Now my heat transfer terms are going to be mass flow rate times h out minus h in. So I have a heat transfer term on the hot side, that's my condenser, and a heat transfer term on the cold side, which is my evaporator. It's important to remember which of these heat transfer terms happens on the hot side and which happens on the cold side, because the energy benefit for the refrigeration cycle is going to be the heat transfer that happens on the cold side, which in this case is the evaporator. Now, the valve is a little bit funny. So it's like a turbine, but it's like a terrible turbine, because a turbine actually produces power. The valve, turns out it doesn't produce any power. The only reason it's there is to drop the pressure. So the assumption that we make, along with all the other assumptions that we usually make for compressors or turbines, the assumption that we make as we go across this valve is that it's isenthalpic. If you don't remember, isenthalpic means that the enthalpy is constant across the valve. So that means that H3 is equal to H4. And if that's the case, what we find is that there is no power produced by the valve. So it's kind of like a turbine, but a turbine that doesn't really do anything. Which kind of makes sense, because I've said that when we keep this power term around, that means we've got some kind of fan blades inside the system, like we'd see in a compressor or a pump or a turbine. But in this valve, we find that it's isenthalpic, so it doesn't produce any power, and it's adiabatic. So really, this isenthalpic valve is also adiabatic. Now, if I want to look at my compressor, this is putting work into my system, so the first law tells me this is a negative number. In my condenser, I'm rejecting heat, so that's a negative heat transfer term. And in my evaporator, I'm accepting heat into my working fluid, so this is a positive value for Q dot. So these are the expressions that I would expect to get for a refrigeration or a heat pump cycle, but you never know what assumptions you'll get asked to make on an exam. It's important to remember that when we're doing a refrigeration cycle, the heat transfer that's the energy benefit is the heat that goes into the evaporator. This is the heat on the cold side of my system. I define my coefficient of performance as the energy benefit divided by the energy cost. If I don't remember what the Greek letter here is, I can just call this COP for coefficient of performance, and I can say refrigeration over here in the superscript, right? I'll denote this as being the actual coefficient of performance because we'll compare this to the Carnot coefficient of performance. So this is going to be defined as the heat transfer on the cold side divided by the net power, but the net power is really just the power consumed by the compressor. So here, my actual coefficient of performance is going to be the magnitude of H1 minus H4 divided by H1 minus H2. These coefficient of performance are always positive, even though here right, we have a positive heat transfer term and a negative power term, but nobody's going to buy a refrigerator if the salesperson tells you that the coefficient of performance is minus 14. That sounds kind of bad. So we just take the absolute value here. If we want the Carnot, or the maximum coefficient of performance, we replace this ratio of heat transfers, because remember we can express W.net as Q.in plus Q.out if we let the first law figure out what the signs should be. And then we can get this as a ratio of temperatures, T cold divided by T hot minus T cold. Now remember here, the numerator is not a delta T, so you need to use absolute temperatures in the numerator. And I would essentially encourage you to always use absolute temperatures when you're finding Carnot coefficients of performance or Carnot efficiencies. So that's a refrigeration unit. What do we do with a heat pump? It turns out the heat pump is basically the same cycle as the refrigeration unit, except our perspective changes. So here, when we have a heat pump, what we're trying to do is add heat to our hot reservoir. So our energy benefit isn't the heat transfer on the cold side anymore. Now it's the heat transfer on the hot side. I can do the same first law. I'll get the same answers for the compressor, the condenser, the valve, and the evaporator. But this time, the energy benefit that I'm interested in is the heat transfer on the hot side. This is the heat that's rejected from the system. Now, if I want the coefficient of performance, the Greek letter that I use is gamma. But again, if I forget it, I can just write down coefficient of performance, or COP. The desired energy effect divided by the energy cost is going to be Q dot on the hot side divided by W.net. Remember, again, W.net is only the power at the compressor because the valve doesn't have any power, or the power is equal to 0 there. If we're working this out from the expressions we had on the previous slide, we'll find that the coefficient of performance for a heat pump cycle is H3 minus H2 divided by H1 minus H2. Remember that our Carnot coefficient of performance for a heat pump looks almost like that of the refrigerator, but in the numerator here, we have T hot because our energy benefit is the heat transfer on the hot side. Again, we got to worry about using absolute temperatures here. So vapor compression heat pumps and refrigerators are essentially the same cycle. We just got to think about what's the energy benefit. But now, we're at the same place we are for all of these cycles in that we've got a bunch of symbolic solutions which have delta H in them. Right? So how do I fix the states for vapor compression heat pumps and refrigerators? So the working fluid here is a refrigerant. The refrigerant is going to act a lot like water did in a Rankine cycle, where we're moving back and forth across the vapor dome. So there are lots of different ways that we can find H or delta H. Typically, we'll look these things up on tables. So here we'll use the textbook tables, but they won't be A2 through 5 or whatever they are for water. They'll be different tables depending on what the refrigerant in our system looks like. Now remember, we're always using different refrigerants. Our friends who are chemical engineers are constantly making more environmentally friendly refrigerants, right? We've moved from Freon all the way up to, I think the newest one I think is called Preon, right? And that's, as we do this, we get more environmentally friendly. There's another new way we're going to look at how to fix specific enthalpies for these cycles, and that's going to be using a pH diagram. So today, we'll learn how to solve these cycles graphically. We can also use the fact that the compressor could be an ideal compressor. And if it's an ideal compressor, remember the compressor is steady state, 1 inlet, 1 outlet, and adiabatic. So if the compressor is ideal, that also means in this case that it's isentropic. So then we can find delta H across the compressor if S out is equal to S in. And then after we fix the real or the ideal compressor, we can move to the real compressor if we're given something like an isentropic efficiency of the compressor. If we try to fix the state across the isenthalpic valve, we need to make use of the fact that it's assumed to be isenthalpic. That means that H at the inlet is equal to H at the outlet. So I said that we'll learn how to solve these particular cycles graphically. And the way we do that is with one of these SUVA tables or a pH diagram. I call it a pH diagram because here I have pressure on the vertical axis and I have enthalpy, it's really specific enthalpy, even though they don't say that, on the x-axis. So you might look at a graph like this and get kind of overwhelmed because there's a ton of different lines on this graph. And that actually helps us, but the first time you look at it, it feels a little bit confusing. But ultimately what this is a scale version of a vapor dome. So we can see the vapor dome here, right? And I apologize, the quality of this is not the best here on the slide, but here we have the saturated liquid line where quality is equal to 0, and here the saturated vapor line where the quality is equal to 1. Now if you look over here, we've got a line for quality is equal to 0.1, 0.2, 0.3, 0.4, etc., all the way to 1. So here's a little bit of background on these pH diagrams. So first, this chart is pressure versus specific enthalpy, even though it only says enthalpy on the x-axis. So we can get almost all of the information we get from tables right on this chart, right? That's why there are so many lines on this chart and why it honestly looks a little bit overwhelming when we look at it. So I talked about this a little bit for enthalpy, but the chart drops the word specific from all of the variable names on the table. So when it says pressure, what it means is absolute pressure. It says enthalpy, but it means specific enthalpy. Temperature is fine, so is quality. But the chart says entropy on the constant entropy lines, but it means specific entropy. And it says volume on the constant specific volume lines. So we have to remember the nomenclature is a little bit different when we look at these tables. So how do I read a graph like this? So first, I can look on the vertical axis and I can find constant pressure lines. So these are going to be horizontal lines everywhere on my chart. If I have a particular point on the graph and I want to find the pressure, I just draw a horizontal line over to one side of the axes. I do have to be careful though, because these are not linear axes with pressure. This is a log scale. So I got to be a little bit careful when I'm looking graphically at the pressure. If I want specific enthalpy and I have a point, I just drop a vertical line down and I can read the specific enthalpy on the horizontal axis. Now here's where things get a little bit tricky. So next, I'm going to look at constant temperature lines. So over here, this says temperature. So here, if I wanted a constant temperature line at -10 degrees, I'm going to drop what looks like vertically over here in the subcooled liquid region. Then I know that temperature and pressure are coincident across the vapor dome. And then now this constant temperature line is going to drop down, right? So I've highlighted some of these in this dashed red line to show you what constant temperature looks like on temperatures that are subcritical, right? That cross through our vapor dome. And some, this is the critical temperature, and then this is a supercritical temperature. Next, we'll look at quality. I already kind of showed you a little bit where these lines are, but quality only makes sense to label under the vapor dome, right? So here we have quality of 0 on the saturated liquid line, quality of 1 on the saturated vapor line, and then as we move here, this is 0.1, 0.2, 0.3, etc., all the way over to a saturated vapor. I think the lines that are the hardest ones to use on this graph are the constant specific entropy lines. So here, the slope changes as we move from left to right. So on the left-hand side of the chart, this is pretty close to a vertical line in the subcooled liquid area, right? Still fairly vertical here, although getting some slope. And then here, as we're saturated vapors, the slope keeps sort of changing here, right? So it goes from here to here. There are these constant specific entropy lines that are marked here. So you just have to know where to look on this graph. Right? Over here, it says entropy, right? But again, what it means is specific entropy. This is in metric units. This says 2.40 kilojoules per kilogram Kelvin. We have constant specific volume lines. They're only shown outside of the vapor dome, and they look, I don't know, almost like blades of grass or long hairs that are sitting on top of the mountain that is the vapor dome. So how do we fix a state using a graph like this? We still need two independent intensive properties. But what's kind of neat about using these tables is each of these independent intensive properties are essentially a line on this graph. So each line is an intensive property. Now, if I have two independent intensive properties, then I should have an intersection between those two lines. And that will give me a point. That's going to be my state point. And if I want to graphically estimate any of the values, then once I have a point, I can look at where the different lines for different properties are. And I can kind of say, well, maybe this is halfway in between these two lines. And I can kind of make a reasonable estimate about what these different properties might be. The most important one for us, because we'll often be worried about first law analyses, is the specific enthalpy. Now, if I want specific enthalpy, then I'll just take my state point and draw a vertical line down and then kind of look where I am versus the points on the x-axis, and I can sort of guess where I am. Or if I want to be more accurate, I can measure what the distance between my two ticks on my horizontal axis are, and then I can measure between one tick and my line where the intersection is with the x-axis, and then I can sort of numerically calculate what the specific enthalpy is. So instead of just talking about it, let's try an example. So here we have R130A. We're adding heat into the evaporator, and we're told that at state 1, we have a pressure of 5 bar and a quality of 0.2. And at state 2, we're still at a pressure of 5 bar, but we have a temperature of 20 degrees Celsius. So how do I find Q dot over M dot for this evaporator? First, I see my control volume is the evaporator, only 1/2 of the evaporator because I'm trying to find a heat transfer rate. I do conservation of mass, and I see that it's steady state, one inlet and one outlet. So M dot in is equal to M dot out. There's only one mass flow rate, so this is kind of what I'm expecting. Here, if I do the first law, I see that it's steady state, one inlet, one outlet. I can neglect the changes in kinetic energy and the changes in potential energy. I'm going to say that this is passive, and I'm going to try to solve for Q dot through my evaporator. I'm going to say that there's no friction or heat losses. So if I do all of this, I get that Q dot is equal to M dot times H out minus H in. Hopefully that's not a surprise at this point in the class. What the problem asked me for is Q dot over M dot, because they didn't tell me the mass flow rate, and that's just going to be H out minus H in. I don't know Q dot over M dot, I don't know H out, and I don't know H in. So it's time for me to fix the states using my SUVA chart. So I know that the two properties I know at state 1 are definitely independent and intensive. I have pressure and quality, and I know I can always fix a state in that case. For state 2, I have a pressure and a temperature. Now sometimes these are independent, and sometimes they're dependent if I'm under the vapor dome. So I'm hoping that state 2 isn't under the vapor dome, because otherwise I don't have enough information to fix the state. So first, let's try to find state 1. So now here I have my table or my chart, and I've sort of looked at or highlighted the saturated liquid line, which is my blue line, and my saturated vapor line, which is my red line. I know that my pressure is 0.5 megapascals and my quality is 0.2. So over here, I see that the pressure on the vertical axis is in megapascals. Here is 0.4, there's 0.6, but I see I have these dashed lines in between. So here it's not halfway in between because this is a log scale. It's a little closer to the 0.6 than the 0.4. But I can see my constant pressure line is going to be at 0.5 megapascals. Now I see that the quality is 0.2. Quality only makes sense to find under the vapor dome. I look here, this, I know it's hard to read here, but this says quality. I want 0.2, there's 0.4, 0.3, 0.2. So my constant quality line at 0.2 is this green line here. So my state point is at the intersection of these two lines. Well, that's good. Now I want to draw a vertical line down and find my specific enthalpy, because that's what I want in my equation, because I know that Q dot over M dot is equal to delta H. So H1 I can find by drawing this vertical line down. Now I'm going to make a bit of an assumption here. It's got to be between 250 and 300. I'm just going to say that this is about 260 kilojoules per kilogram. Right? I don't have a ruler here. I didn't measure this, but I think that this is kind of a reasonable estimate. Right? It's certainly closer to 250 than it is 300. Now the weird thing is if I fix this state in the textbook, I get that H1 is 108.8 kilojoules per kilogram. Right? Now, if this was only off by a little bit, I could sort of chalk that up to graphical error, but 108.8 is over here, right? It's maybe not even under the vapor dome. So what's the deal here? Why are these different numbers? So it turns out that the datum, the 0 point here for specific enthalpy, is different on the table and on the textbook, right? So it's a little bit weird, right? It's a little bit like how, for pressure and temperature, we have relative pressures and we have absolute pressures. Relative pressures are relative to some 0 point, which is at least somewhat arbitrary. Even with pressures, a gauge pressure is going to change depending on where you are. So if you've got some storm rolling in, your atmospheric pressure is going to be different, but your gauge pressure always only measures relative to the local pressure of the atmosphere at the particular time where you're taking the measurement. So in this case, my H values are different because my datum or my 0 point is different, right? So here I'll explain that in the text. So the textbook has a different 0 value for a specific enthalpy than the handbook, right? So this picture is taken from the FE handbook, but you could also find it on like the DuPont website. So DuPont is a company that makes different chemicals, including the refrigerant that we're using for this particular problem. So since both references have different values, even though they have the same unit, we can't take the same number from the textbook and subtract it from a number from the table, right? Because they're offset. That's like that would be like adding a gauge pressure to a absolute pressure, right? And pressure is kind of a good analogy here because pressure is measured in the same units, no matter if you're using gauge pressure or absolute pressure. So this is kind of similar. We just have a different 0 point. So the textbook values are always about 150 kilojoules per kilogram lower than the handbook values, or the values that I'm pulling off this table. Practically what this means is that we can never do a problem halfway with the table and halfway with the chart. We got to pick one method and stick with it. If you see this on an exam, I'll tell you which method I want you to use, right? Our difference here was just over 150, so our graphical reading is not too bad over here, but we do have some error because we're just reading this graphically off the table. So obviously doing this has more uncertainty involved than if we were interpolating on a table. So we found state 1. Now let's find state 2. Here we have a pressure of 5 bar and a temperature of 20 degrees. So here at state 2, I know the pressure is still 0.5 megapascals. So I draw this same horizontal line that I drew for state 1. Now for state 2, I know the temperature is 20 degrees. So it's a little tricky to look at what these temperature lines say, but here's 0. If I go left of 0, this is negative 10 and negative 20. It's a little tricky because this is right where they write temperature. So you might be confused and think this is the 20 degree line, but the 20 degree line is really over here. So here I'm coming down. I hit the saturated liquid line before I hit my pressure of 0.5 megapascals. So that means that I move horizontally over here, parallel to this 0.5 megapascal pressure. And then I dive down after I move past the vapor dome. So my state 2 is in the superheated vapor region here. I draw a vertical line down, and I'm going to estimate that H2 is 412 kilojoules per kilogram. If I did the interpolation in the textbook, I would again see that the number is not the same. Here it was 260.4 kilojoules per kilogram. So I can now take the numbers that I have and put them into my first law to find the heat transfer rate added to the evaporator over the mass flow flowing through the evaporator. I know H out and I know H in. So I can use that to find Q dot over M dot. So I'm going to show you this two different ways because I kind of made the argument that it doesn't matter if we do it all on the chart or if we do it all in the textbook, we should get an answer that's basically the same, accounting for any graphical errors when we read it off the chart. So here, if I do Q dot over M dot from the table, I get 152 kilojoules per kilogram. If I do it from the textbook, I got 151.6 kilojoules per kilogram. So this means that I did a reasonable job of reading these values off the table. Or at least that I made errors consistently in the same direction, right? So I got basically the same answer here, which is pretty good. So if I ask you to do this on an exam, I'm not going to be super concerned with how accurate your numbers are. What I'll want to see is what your process is, and I'll also ask you to submit the pH diagram that you worked off of so I can see how you went about fixing these states. So that's it for our introduction to vapor compression refrigeration cycles. Our last formal lecture, which is kind of new material before we get into exam review, we'll be going through an example for a vapor compression heat pump. And we'll do that next time, and I'll see you then.